Imagine a bolt hole pattern that fits perfectly onto a mating flange, yet when you measure those holes individually, they're not actually evenly spaced. Welcome to The Explainer. Today, we're diving straight into the ASME Y14.5 2018 standard to demystify advanced pattern controls. If you've ever looked at a complex engineering drawing and felt your head spin at the sight of stacked feature control frames, you are in the exact right place. We're going to completely break down composite position tolerancing. So here is the million-dollar manufacturing paradox. You've got a flange with a 6-hole bolt circle, and it drops right into its assembly. It fits perfectly. But when your quality department measures those 6 holes on a CMM using strict coordinate measurements, they fail. So why does the part still assemble correctly, even though the holes are not perfectly located relative to each other? Well, it's because a single position tolerance can control overall location, but it can't always intelligently control the internal structure of a pattern. Okay, let's dive into this and solve this engineering mystery step by step. We'll start with the whole pattern paradox, introduce composite position, break down the upper and lower segments, compare composite to single segments, look at functional gauging realities, and wrap up with the latest Y14.5 2018 standard updates.
Starting off with Section 1, the whole pattern paradox.
Now, we all know the standard feature control frame, right? It acts like a sentence in GD&T. It gives us the geometric symbol, like position, the tolerance zone shape and size, material condition modifiers, and finally the datum references that lock down our coordinate system. For a single independent hole, this is absolutely perfect. It creates a nice cylindrical tolerance zone centered exactly at true position. But here's where the basic framework hits a wall. Standard position tolerancing treats every single hole as an isolated, independent feature. And when you're manufacturing something complex, like an engine block, a hydraulic manifold, or a precision aerospace flange, treating holes independently completely ignores functional reality. It fails to control the relationships between multiple holes. We need to control how the entire group of holes locates to the part, sure, but we critically need to control how the holes relate to each other. Relying on a single positional tolerance often just over-restricts manufacturing and drives up costs without making the assembly any better.
Which brings us to Section 2, enter composite position. So, what is it? A composite feature control frame is basically a single geometric symbol that spans across 2 stacked tolerance zone frameworks. That single shared symbol is the dead giveaway that you're looking at a composite tolerance. Both of these segments apply to your part at the exact same time, but they serve completely different functional purposes. Together, they create this brilliant balance between making sure your part aligns with a larger assembly while maintaining strict internal accuracy for the pattern itself.
Let's look at how this actually works in Section 3, upper versus lower segments.
And this brilliantly illustrates the mechanics. The top half is called the Pattern Locating Tolerance Zone Framework. Think of this upper segment as the boss. It controls the entire pattern as a rigid unit, dictating its overall location and orientation relative to the specified datums. The bottom half is the Feature Relating Tolerance Zone Framework. This lower segment is a refinement. It doesn't locate the pattern at all. Instead, it tightly controls the feature-to-feature spacing and the orientation within the pattern itself.
If the acronyms feel a bit heavy, just think of the stencil analogy. Imagine you have a plastic stencil with a pattern of holes cut into it. The upper segment determines where on the piece of paper you place that stencil. You can shift it around or rotate it slightly as a rigid group. But the lower segment, that represents the physical plastic of the stencil itself. It ensures that the spacing between the actual cutout holes stays perfectly intact and functional no matter where the whole stencil got shifted.
Moving on to Section 4, composite versus single segments. Now this is a notorious point of confusion. Engineers often mix up composite position with multiple single segment tolerancing. Notice the clear functional distinction here. In a composite frame, you've got one shared geometric symbol and the lower segment controls orientation only, allowing that stencil to float. The frameworks operate together. But in multiple single segment tolerancing, you have 2 independent symbols. The lower frame operates completely independently and controls both location and orientation. Using multiple single segments when you really just needed composite refinement can severely over-restrict your machinists, literally forcing them to hit a location tolerance twice. So, let's bring this down to the shop floor in Section 5, functional gauging realities. So the crucial point here is what happens when we pair composite position with the maximum material condition, or MMC modifier. Magic happens for manufacturability. MMC sets the worst-case mating boundary,
For a hole, that's its minimum size at its worst positional location. But here's the best part. As the machinist drills that hole a little bit larger, moving toward least material condition, they earn what's called bonus tolerance. That expanding tolerance allows the hole center to drift a little more out of position while still guaranteeing the bolt will pass through, and this directly enables the use of physical fixed go-no-go functional gauges.
If you're designing a functional gauge simulator for an internal hole pattern, the math is incredibly straightforward. Step 1. Identify the minimum diameter of the hole. That's your MMC. Step 2. Identify the true position tolerance from your feature control frame. Step 3. Simply subtract the true position tolerance from the minimum hole diameter. The result is the exact diameter you need to machine your fixed gauge pins. If the part drops onto those pins, your composite internal pattern refinement is absolutely good to go.
And just a super quick note for external features, like a pattern of mounting pins, the logic is exactly the same, but the math just flips. To design your gauge block, you take the maximum diameter of the pin, your MMC, and you add the true position tolerance. That gives you the exact diameter for the holes in your checking fixture. Finally, let's look at Section 6, Y14-5 2018 Standard Updates. If you've been working with older standards, you'll know this is a massive shift. In the 2018 update to ASME Y14.5, concentricity and symmetry were entirely eliminated, just gone. Why? Because they lacked reliable measurement repeatability on CMMs and caused endless confusion on the shop floor. So what do we use now? Position and profile. Position, particularly composite position, is now the absolute gold standard for controlling coaxial features and complex geometries.
As the standard states, deletion of the symbols does not leave industry without a means to control features, but it does eliminate the confusion. And that aligns perfectly with what we're talking about today. The goal of GD&T isn't to create complicated drawings, it's to create clear, undeniable definitions of design intent that a machinist can actually hit.
Which brings us to our final thought. The paradox we started with is officially solved. A part assembles because its internal spacing, its functional refinement, is protected, even if the whole pattern shifts slightly on the part. So I want to leave you with this. If GD&T is ultimately about defining true functional intent, how will separating your overall pattern location from your internal pattern refinement transform the manufacturability of your next design? Thanks for joining me on this explainer. Keep those tolerances functional, and we'll see you in the next deep dive.